Greetings, guys. Time to talk about rationalizing denominators. Okay, so before we get into the real problems, let's go over a couple of things with radicals that you'll need throughout this section. Okay, now I'm giving some examples here. I want you to get the ideas, not just the individual numbers, because obviously 5 times 5 is 25. That's given already. But here's the skills that you'll need to succeed in this section. Okay, remember that when you multiply two of the same square root, that you end up with the value underneath the radical there. Right here, 5 times 5 gives me 25. But the key link here is to remember that that's 5 squared mixed with the square root. And those tend to undo each other, right? But just by definition, of course, the square root of 25 is 5, and that's where we get our answer, okay? More generically, any power with any root of the same value is going to have that same ability. So if I have a third root, right, as long as I have 3 of them, because it's a third root, then I'll end up with the same kind of property here, right? So the third power mixed with a third root gives me this kind of cancellation. And I hesitate to use that word, but I know you're all familiar with it. Okay? And then same thing with variables. With variables, it's just about counting, right? If I've got 2x's multiplied and 3x's multiplied, right? Multiplying those together gives me 5 total in this case, to match the 5th root, and therefore I get just the x, because those are opposite operations. Okay, so just keep in mind that what we have is the ability to basically make a radical give itself up, right? If I were able to match it with enough of its own other of the same pieces, right? Okay, and then another skill that you'll need a little bit later in this section is the definition of conjugates. Right? Let's write that one down. Conjugates. And that would be these two pieces here. The a minus b and the a plus b are called conjugates of each other. And the special property of conjugates is that anytime you multiply conjugates, you get a difference of squares. And I know you've seen that before because it's just the opposite of the way we use it with factoring, difference of squares. Here the idea is you may have one of the two conjugates and you'd want to bring in the other one. So for example, if I were to multiply 4 minus the square root of 7 with 4 plus the square root of 7, foiling that out, or multiplying everything to everything as we always say, then the inner and outer pieces, right, the 4 square root of 7 and the minus 4 square root of 7 are going to zero out. And you're just left with the 4 squared and the square root of 7 squared, which you'll notice doesn't have any radicals in the answer. And that's sort of the goal here in rationalizing, right? The word rationalizing comes from making something rational, which a lot of times the radicals that we don't want to mess with are not rational, like square root of 5 and third root of 4, and so on and so on. Okay? So the idea here is that we want to find crafty ways of getting rid of radicals in places where we don't want them. And that would be the skill of rationalizing. Okay? Okay, so here we go. I have a fraction here in the 7 over square root of 2 problem. And there's a radical in the denominator that I can't simplify any further. I don't want the radical in the denominator, and there's several different reasons why this might happen in a math course, be it common denominators or even in the old days when they didn't have calculators and they wanted to find a better way to do these divisions by hand, and radicals make that a lot more difficult. For whatever reason, there's several reasons that come up in other math classes. We don't want the radical in the denominator, okay? So as we saw in the beginning reminder skills over there, what we would want to do is multiply, because fractions allow me to multiply the numerator and denominator at the same time, as long as I don't do two different things. So in this case, what I want to do is multiply by square root of 2. Because I know from that skill we talked about earlier that if I duplicate a square root, then I'll end up with a value that doesn't have a radical. But to make it fair and balanced, whatever I multiply in the bottom, I've also got to multiply in the top. So I'm basically multiplying square root of 2 over square root of 2. Basically, I'm multiplying by a value of 1. All right, so then what happens? Well, let's see. This is just going to be 7 square root of 2 now, divided by square root of 2 times square root of 2 is square root of 4, which is just 2. So you can see what we have now does not have a radical in the denominator, and that's what we wanted. We have rationalized our denominator. Okay? Next, I have a slightly more complicated problem there. Just a few more pieces working in there. The first thing I'd want to do is simplify any radicals that are in there, if I do happen to have some that can be, right? In this case, square root of 9 and the square root of 16, I can actually do those, so you should. I'm going to get 2 times 3 in the top, and 4 times the square root of y in the bottom. Okay? I can reduce the 2 and the 4, and what I end up with is 3 over 2 square root of y. All right, so where I'm at now, I still have my issue though. I don't want radicals in my denominators. So the next thing that I have to do is multiply by something that will allow this to not be there anymore, right? So what I'm going to multiply by, just like earlier, is I'm going to match just the radical piece, just the piece that's causing the issue. So here, I multiply by the square root of y. I'm just duplicating my value, right? Okay, but I can't just do that in the denominator. I've got to match it in the numerator. So I'm essentially multiplying by 1 still, right? And I can proceed from there. That's going to give me 3 square root of y divided by the 2 is still here, and then square root of y times square root of y is the square root of y squared, or just y. And then I don't have a radical in my denominator there anymore either. And I can't simplify anything else. Just on a side note, if you hadn't simplified beforehand, the trick would still work, the method would still work, but you'd have a lot more pieces to simplify afterwards, because you'd basically be duplicating a lot of pieces that could have been already simplified before you started. I find this the most efficient way, but if it makes sense to you to start out rationalizing first, go ahead and give it a try. Maybe for some people that would make more sense. Okay? And then in the bottom example here, the third root, right? Same kind of trick though, don't forget. Same kind of method. I'm going to be taking this third root here, and what I want to do is rationalize the bottom if it needs to be. Well, right now the fraction's in the radical. And don't forget, we can split that up, right? Radicals can be split up over these things. So I have the third root of 2 over the third root of 25. Okay? Then I would see if I could simplify any radicals in their current form. Well, 2 is prime, so no. And 25 is just 5 times 5. That's not going to reduce since I need 3 things in the third root, right? 3 things multiplied in a third root that are the same to simplify. Well, then that's our key right there, right? 25 is already 5 times 5. Right here. So if you're looking at the trick at the very beginning of the video, you would think, oh, well, I need 3 of these third roots of 25. And you could work it that way, but it would be overkill, because you'll notice I've already got 2 5s under this third root. Remember, for a third root, I need 3 of the same thing. I only need to bring in 1 more 5, and then that would match this up. So I'm going to multiply numerator and denominator by the third root of 5. Because notice what that will do is give me 5 to the third in the denominator. Or if you're coming at it from the holistic approach, what I would do here is this would become the third root of 10 over the third root of 125. And as you would know, 125 is one of your third root numbers, one of your third power numbers. So then I could simplify that into the third root of 10 just over 5. Therefore, I don't have any radicals in my denominator, and it has been rationalized. All right, 2 more examples. Square root of 5m over 11n. Okay, so just like in our last one, I'll have a whole radical, and I want to split it up, right, into the 2 pieces, the numerator and denominator. The numerator I'm not much worried about because it's the denominator I want to rationalize. Like so. And of course, I don't see any other radicals that I can simplify. I would if I could. At this point, the square root of 11n is the difficult part here, is the part giving me the issue. So that's the thing that I'm going to use the method on. It's a square root, so I only need 2 of them. I'm going to multiply by 11n square root. And I'm going to have to do that to the top and the bottom. So at this point, I've got in the numerator square root of 55 mn. I know, kind of a messy radical, but you know what? That's the price you pay for cleaning up the denominator. The numerator just gets a little messier. And then, of course, in the denominator, I've got the square root of 11n times 11n, and since there's 2 of them, right, squared and square root, opposite operations, I end up with just 11n. All right, and then this other example here, I've got 5th root of a squared over 5th root of 32 b to the 12th. So like always, I look for what can I simplify first. So I'm noticing a squared, there's not enough a's under that radical to simplify, so I'll leave him alone. Here, 5th root of 32, 5th root of b to the 12th, there are some pieces in there I can simplify, right? If you go down your 5th power list, you remember 32 is 2 times 2 times 2 times 2 times 2, 2 to the 5th. I can actually do the 5th root of 32 straight out. I can simplify that one. B to the 12 is another one that I have a few pieces I can do. Remember, the trick to that is the fact that 12 is bigger than 5, right? So I can find a number 12 or less that's perfectly divisible by 5, and I would be able to separate it out and actually do the power over root division and get one piece clean away. Let's do that. Let's simplify here. I've got 5th root of a squared, and in the bottom, 5th root of 32 is just 2. And the b to the 12, I'm going to split that into 5th root of b to the 10 and 5th root of b squared. And remember, the reason is because I'm picking a number just less than 12 that will divide by 5. 10 divided by 5 will work perfectly for me. So after simplifying, I end up with the 5th root of a squared over 2b squared. 10 divided by 5 is 2. And then I still have this 5th root of b squared also. Okay? All right. So now I'm to the point where I've simplified as much as I can, but I've still got this radical in my denominator. I want to not have that there. Okay? So at this point, I'm noticing I've only got 2 multiplied b's here, and it takes 5 of them to make an entire grouping under a radical that works. Okay? So all I need to do is bring in that many more that will level me out to 5. I have 2 of them. So now I've got to multiply the 5th root of b cubed. And therefore I have to also do that in the numerator. Okay, let's see what happens here. The top is going to be the fifth root of a squared b cubed. The bottom is going to be 2b squared times, this is the fifth root of b to the fifth. So that will be just b. Therefore, my final answer, fifth root a squared b cubed over 2b cubed. So now we switch gears slightly. I'll be rationalizing denominators here, but the denominators aren't simple monomials anymore. Here they're binomials, meaning they have two terms that are being added or subtracted, right? So if you try to employ the trick that we were just using, you'll find that all it does is make a mess of things. Instead, what I need to use is the conjugate skill that we talked about at the beginning of the video. Since these already start out as half, one conjugate, half of a difference of squares, all I need to do is bring in another one, okay? And again, notice, these are all square roots, right? For cube roots, we have cube conjugates, but that's another story for another day. So here, what I need to multiply by is his own conjugate. 2 square root of 5 plus 1, so his conjugate would be the same terms, but with a subtraction. So that would be 2 square root of 5 minus 1. Like so. All right. In the numerator, whenever I have something that was a monomial like this, I leave it alone at first. I don't multiply it out, because it is possible I might be able to simplify something later. Okay, so what I'm going to do is I am going to multiply out the denominator. So I've got 2 square root of 5 times 2 square root of 5, which is 4 times 5. Let's go through that one more time, right? The 2 times 2 is 4. Square root of 5 times square root of 5 is square root of 25, which is 5. I've got a minus 2 square root of 5. I've got a plus 2 square root of 5. And I've got a minus 1. As we said before, the two radical pieces here are going to add to 0. And I'm left with 4 times 5 minus 1. So for my final answer, I'm going to have 3 times 2 square root of 5 minus 1 all over 19. Okay? And it's perfectly fine to leave it like that. If it makes you feel uncomfortable with the 3, out there. Like I said, remember, the only reason I did that was just in case it would reduce with whatever was down here. Since it doesn't, it's fine to leave it like that. Some people might think that's a little messy. And if you are thinking that way, then go ahead and distribute it. It really doesn't matter either way. Either one of those is a perfectly acceptable answer when I grade. Okay, next. Square root of 5 plus 3 over square root of 3 minus 2. All right. I'm going to ignore the top. Remember, the numerator is not the problem here. I want to rationalize the bottom. It is a binomial again, which means I'm going to employ the same trick right here, the same method. I'm going to use its conjugate, right? What's its conjugate? It has a minus, right? So naturally, I'll be using the addition. I'll be multiplying by square root of 3 plus 2. That's its conjugate. Now in the numerator here, it was already a binomial also. That's different than last time. I'm going to multiply out both the top and the bottom this time for any hopes of anything good. Okay, so here we go. Square root of 5 times square root of 3 is square root of 15. Then 2 square root of 5. Then 3 square root of 3. Then 3 times 2 is 6. And And in my denominator, I've got square root of 3 times square root of 3, which is 3. Square root of 3 times 2. And negative 2 times square root of 3. And negative 2 times 2. Just like before in the denominator, the radical portions add to 0. And then I notice the 3 minus 4 can be combined. In the numerator, no radicals are alike, and nothing can be simplified further in this case. So the numerator is going to stick around like it is. Okay? So I've got square root of 15 plus 2 square root of 5. That's not going to fit. So let me go ahead and scooch down. Okay? Square root of 15, 2 square root of 5, 3 square root of 3, 6, all over negative 1. And the nice thing about this is anything divided by 1, of course, is itself, and then I just need to distribute the negative. So I can actually simplify this a little bit by saying negative square root of 15 minus 2 square root of 5 minus 3 square root of 3 minus 6. Right? Okay. All right, now the last example here. Same idea. I have a binomial in my denominator. Really, the only difference with this one is that there's a variable under one of the radicals. So in this case, let's think about what my conjugate would be. Okay? So I'm going to be multiplying this denominator by 2 plus square root of x, because that's its conjugate. That means I'll also be multiplying that up here. And remember, the first time, when I had a monomial up here, I sort of leave it alone at first, just in case there's something I can simplify, right? So in my numerator, I've got 4 square root of x, 2 plus square root of x. And in the bottom, I'm multiplying out. So I've got 4 plus 2 square root of x minus 2 square root of x and minus x. Be careful you're seeing that, right? Square root of x times square root of x. Square root of x squared, that's just x. As before, these add to 0, and I'm simply left with 4 minus x in my denominator, which is not going to really simplify with anything up here. So I go ahead and multiply that out. I distribute it out, right? That's going to be 8 square root of x in this first multiplication, and then 4 square root of x times square root of x. 4 times 1 is 4. Square root of x times square root of x is just x again. And then this is where you would stop. Okay? So I hope this was helpful in your endeavors to learn to rationalize denominators.